Hello, I'm Allan Kennedy, and I'm going to be talking about how I use Python as a Shlaer-Mellor action language. Now, in what follows, believe it or not, I'm genuinely going to attempt to say as little as possible, because there's a lot of stuff, it's quite dry, and you'll fall asleep. So therefore, please do pay close attention to the presentation material. You're all Shlaer-Mellor experts, it's just Shlaer-Mellor stuff, so hopefully you'll find it entirely straightforward to follow if I don't say too much. Let's find out. Imagine a situation where you're doing Shlaer-Mellor, you're building domain models using xtUML, but you're doing so in an agile environment, and there's an expectation that you're going to deliver on a regular basis a working deployable increment on the existing system. But you don't have a code generator, and action language is unfamiliar to the client, doesn't run on his environment anyway. So what are you going to do? In my case, because Python comes as standard on a Macintosh, which is my development environment, then it was a pragmatic no-brainer to attempt to adopt Python as an action language for Shlaer-Mellor. And if you put Python together with xtUML to form an action language, then of course what you get is called PyxUML. Now, even though, because notwithstanding that this is an entirely pragmatic decision, there are some principles involved, clearly. Court and I were discussing this back in August when Court asked, do you follow any special rules? Do you follow some kind of Shlaer-Mellor idiom? And to me it was obvious that that would be the case, so I said, gushingly, yes, of course. The action language must operate solely with Shlaer-Mellor semantics and reference only problem domain concepts and terminology. The fact that it's Python should seem completely unobtrusive and seem entirely natural in the context of a Shlaer-Mellor action language. And of course, PyxUML should be specified and implemented using PyxUML. Court sounded enthusiastic. This is great, he said. It will be of interest to our community. Well, I certainly hope it is. I'm sure you'll let me know in due course. Now, those of you fortunate to be Bridgepoint users, I'm told, will be intimately familiar with the microwave oven as a tutorial example. So here is a microwave oven. Maybe not quite as you know it, but it's the same. It's based on the Bridgepoint one. One of everything, so no interesting navigations. Pretty cheap piece of kit. Can just do the usual things with it. Here's the collaboration diagram, and it's apparent that the interesting behavior is in the oven itself as it tries to synchronize its component parts. So here's the oven state model. I'll let you just read it and get a feel for the look and feel of PyxUML action language. And I'll comment on one or two items which are part of PyxUML. First of all, every state begins by invoking enter state. In ASL, we used to use language like generating an event to an instance. In PyxUML, we talk about an instance accepting an event. Enter state will return event parameters if there are any. And there are timeouts, which effectively specify a maximum dwell time in any particular state. When we send a self-directed event, we don't use accept, we use internal. And if we want to specify that an event is going to occur in the future, we use timed event. In this case, this oven will accept a decrement remaining time event in one time unit in the future. Okay, I hope that seemed fairly obvious, and I'm not sure what your opinion would be, but my feeling is that notwithstanding that this is quite a simple example, this style of action language is succinct and readable and pleasingly obvious. So here's a complete specification of the oven. Yes, the oven. There's the oven in the information model. Here's the oven state model. And what I want to draw your attention to is the state transition table. This is an IUML feature. I genuinely don't know if Bridgepoint does this, but it presents a complete picture of every combination of event and state so that we can take care to specify explicitly what happens for each combination of event and state. And the reason why I want to draw you to be aware of that is because here is the code which sets up an oven class and its instances. This is very much a what you see is what you get situation. What you saw in the code is what you saw in the model is what you get in the code. Precisely the same attributes in the microwave model and the microwave code. Now the relationship between a class and its instances is realized as a Python dictionary. The instances are a dictionary which are keyed on the preferred identifier and map to the instances themselves. The state transition table is a dictionary keyed on state and event and mapping to the effect. Reporting and logging are about visibility of execution, and here's the initialize state transition table routine. Every active class has one of these, and if you look at the events, the states and the effects, you'll see they're just a transcription of the state transition table that was part of the model. Now, every class has an ID. In the case of the microwave oven, the ID is the oven serial number, and that will act as the key for the instances mapping to the instance itself. Now, the door, the turntable, the light and the beeper and the magnetron are all referential attributes taking as a value the instance handle returned by these creation routines. If the referential attribute is formalizing a many association, it will be a dictionary. We'll talk more about that later. Here's a test routine for the microwave. Kick off by setting up some printers to provide us with some visibility of the execution. Create an oven with a serial number of 111 and a delay of 5 seconds. This is what we're going to do. Here's the code which does it. Set the timer running and run the domain. Done. Here are the results. The report shows at what point in time an instance changed state. The door became open at t equals 2 seconds, which is what we planned. The door is closed at 7 seconds, which is what we planned. There it is. and the whole execution sequence is 30 seconds in length. Meanwhile, trace tells us at what point in time an instance in a particular state accepts an event. Remember, the instance doesn't necessarily perform a transition depending on what's in the state transition table. Okay. I hope that made sense, and I hope it wasn't too brief. Now, let's take a look at PyxUML as a modeling formalism and a runtime. In this diagram, it's primarily modeling formalism, and there shouldn't be any surprises. If you cast your eye over this, it will seem quite familiar. But there's one particular way in which PyxUML diverges from classic Shlaer-Mellor. Of course, the domain model specifies that there are associations between classes. Each association consists of two links. A link from a class and a link to another class, or possibly the same class, of course. Links have multiplicity and are formalized by a single attribute which is referential. If there are many instance handles, a referential attribute can have many instance handles as its values. Its multiplicity will be many, and it's realized as a Python dictionary. Otherwise, I think there's nothing that is particularly distinctive about the modeling formalism. After all, I'm using a Shlaer-Mellor modeling tool. Over here on the runtime side, the runtime domain has active and passive classes. These are runtime classes. The runtime classes have instances, many instances held in a dictionary. Each runtime instance has an ID and holds its attribute values in slots. For those of you who aren't aware, the nice thing about slots is that you can't add or delete attributes at runtime. It's fixed, just as Shlaer-Mellor suggests it should be. There will be passive instances, active instances and printer instances, timeouts and timers, events, timed events. At runtime, an active runtime class holds a state transition table, which you have seen, which specifies that in some cases there will be transitions which will invoke an action which executes in a specific state. Note how the effects and the transitions, the actions, the operations and attributes are not just part of the model, but also part of the runtime model. Let me mention in conclusion, there's one other thing I would like to draw your attention to, which is that PyxUML is specified and built with PyxUML. So, just as we have, for example, active instance in the model, when we look at the class browser for the code, we find active instance is actually part of the runtime, along with event, timeout, timer, printer, and of course the classes in the domain model. Now, I was going to mention that in this formalization of the PyxUML runtime, I think it's apparent that Shlaer-Mellor concepts and terminology are pervasive. They're everywhere. It's clearly a Shlaer-Mellor runtime. But there's a contrast with this runtime model. This last year was described as a Shlaer-Mellor architecture. I don't doubt that it is. But Shlaer-Mellor concepts and terminology barely appear. There's a domain here and an event down here, an event parameter here, but that's it. I found that very odd at the time and still do. I don't want to digress with this now, but I'm flagging it up as something that might make an interesting discussion within the community subsequently. Now, I promised you a more sophisticated example so that we can look at richer Shlaer-Mellor content. This is a training course case study. It's a helicopter maintenance workshop simulation. I'm not going to use up time to talk through it in detail. I'm just going to draw your attention to the interesting features. First of all, it has assigners because there's resource contention. There is not an infinite supply of spare engines, therefore there's contention for spare engines. The simulation is intended to establish how much engineering resource we need to achieve a certain degree of availability of the helicopters in a fleet. So there's contention for engineering resource. We need assigners for that. There's a super subtype hierarchy. Engineered items can be an assembly or a part. Assemblies can be subsystems or platforms. Of course, the helicopters are platforms and their unreliable engines are subsystems. When an assembly is assembled from engineered items and engineered items are installed in a parent assembly, we get an installation. We're going to focus on the installation and in particular how we navigate the super subtype hierarchy and how, when this operation, waiting for the deinstallation team to finish, is occurring, we want to navigate from the installation to the component engineered item to the engineered item type all the way up to the configuration item where we will find a deinstallation time. And when we are commencing operation, in the simulation all the installation has to do is to predict when it's going to fail. So we'll need to navigate from the installation to the component engineered item, the engineered item type, where we'll find the mean time between failure, the standard deviation, minimum and maximum repair times. But first, let's look at the installation assigner. I'll pause a moment to give you a chance to read the action language in the busy state. So, some platform is requesting a replacement subsystem, so the assigner will say, tell me who's requesting a replacement subsystem. This is what in ASL would be a find statement. The requesting platforms are those platform instances for which the current state is requesting a replacement subsystem. If there's at least one, select one at random. In passing, that's a bonus of using Python. All the Python libraries are available and this comes for free. Now find whether we have any spare subsystems. The subsystem stock are those subsystem instances for which the current state is spare. If there's at least one, pick one at random and create an installation which will an installation of the selected subsystem in the selected platform. Initial state awaiting platform availability. and then you're done. I hope that seems familiar to all those of you who remember the optical disk management cabinet. And here is the state model for the installation. Let's look at the commence operation action first. Remember, in order to predict the time when a failure will occur, we have to navigate to the installation's component item type. Subsystem type is installation component item type. So the mean time between failure is there, standard deviation is there, there's the repair threshold, there is the predicted time to failure, timed event to occur when the predicted time of failure to failure has elapsed, subsystem has failed, in which case we'll await some deinstallation resource, so we fire off a message to the installation resource allocation assigner, and when the resource is allocated, we have to navigate to the configuration item to find the deinstallation time. In ASL, this was a beautifully elegant concept called correlated associative navigation, and this is how it's working here. The parent item type ID is this installation's parent engineered item type ID. You probably wanted to see the diagram when I said that, but take my word for it. The component item type ID is this installation's component item type ID. We now have the key for the configuration item. So the configuration item we want is the engineering configuration item instance with that key. And there is the deinstallation time. All too brief, but I hope you get a feel for the relative clarity and succinctness of PyxUML action language, and I'm looking forward to your feedback in due course. Now, this is what you get when you execute that model. Here's an example of a subsystem failing and a platform requesting a replacement subsystem. It takes place 11 days and 10 hours into the execution, and precisely 24 hours later, platform ELK7 is once again serviceable. Why? Because right at the beginning of the simulation there are spare engines. So all we have to do is to spend 12 hours deinstalling the broken engine, and then 12 hours installing a spare engine, and bingo, we're serviceable again. But sometime later, ELK7 is requesting a replacement subsystem again. We're 26 days and 13 hours into the simulation now. And it's over 2.5 days later that ELK7 is once again serviceable. Why? Because the engineering resources were busy and there were no spare engines. They're all in use or being repaired. And so it simply took longer. For what it's worth, in that particular simulation, there was one mobile repair and service detachment which performed 389 installations and deinstallations but didn't do any repairs. There are 5 repair teams at the factory who each performed this number of repairs, spending about working nearly 12-hour days to do it. As a result, Each helicopter demonstrates in the order of 80% or more availability in the period, and the overall fleet availability was 82%, and we can tell you that on 87% of the period, more than 7 helicopters were available. If we were to drop the number of repair teams down to about 3, then the availability goes down to around 70%. And they have to work 18-hour days. Now, let's begin to wrap up. PyxUML has a worldwide user community of 1, which means that there's not going to be an enormous number of projects that one can point to where it's been used, but it has been used. The maintenance workshop was done back in 2015 as work on the MOD's logistics and supply chain. And then the following year, a genuinely challenging and complex simulation of the communications network which underpins the smart meter rollout. The challenge was to discover what business scenarios would cause the network to fail if it wasn't enhanced sufficiently responsively. Then after that, a very big combinatorial data challenge with the NHS pathways triage algorithms. These are enormous interconnected decision trees with lots and lots of redundancy and unnecessary complexity, and formalizing the underlying information model using PyxUML in order to write analytic tools was immensely powerful and successful. Currently, all of this is being used to do traffic analysis and volume prediction based on GPS data, which is intended to make a contribution to lockdown policy in relation to how interconnected parts of the country are, which might be hotspots or cool spots. It's interesting to reflect on the relative history and timeline of both Shlaer-Mellor and Python. And interestingly, it turns out, of course, they both emerged from the same era in computer science and software engineering. And it's interesting to speculate on how things would have turned out if the Shlaer-Mellor community hadn't focused on action languages and inventing new ones and reinventing them and building code generators. What if instead they'd simply adopted Python as an action language? Now you're in a position to have already formed a view about whether the PyxUML's use of Python read like an action language and whether it satisfied the principles that I articulated earlier. But imagine what it could be like. Contrast the size of the worldwide Python community with the size of the worldwide action language using community. And I can't help but think, this is possibly controversial but maybe worthy of debate, I can't help but think that if the Shlaer-Mellor community had not been so fixated on translation, but instead had emphasized the strengths of Shlaer-Mellor as a rigorous framework for organizing our thinking and formalizing our understanding of a problem domain, and therefore we simply adopted a suitable language like Python to provide executability, then things might be very different. To finish off, let me draw your attention to these Python aphorisms. I guess they could be described as Pythonic, but frankly, I see no reason why they can't be described as Shlaer-Melloric. I particularly like the last one. There should be one, and preferably only one, obvious way to do it. I agree. Thank you for listening. I hope you've enjoyed it. I hope there was something there of interest and something that you might want to follow up. In the meantime, I'm ready and waiting to be shot down in flames by your questions. Thank you for everything.